So good evening, everyone. Dr. Ashby, thank you again. Dr. Ashby is a researcher from Australia on the topic of myopia, an expert on this field. And please, Dr. Ashby, go ahead.
Thank you very much. Now, feel free, as I'm going through this presentation, to actually stop me and ask any questions. Don't feel you have to wait to the end if you've got a burning question. I'm happy to pause at any point and discuss anything I put up on the slides.
Okay.
So once again, thank you for both Professor Ian Morgan and myself being invited to give this talk on the use of Levodopa to control myopia progression. What I'll do through the first half of this talk is simply give you some background information as to why we would think to use Levodopa for the treatment of myopia. And then I'll provide you some preclinical evidence of its effectiveness at treating myopia, and as well as preclinical and clinical safety data showing the use of Levodopa as a topical ocular formulation. Okay, so as most of you will be aware, myopia is due to a mismatch between the refractive powers of the cornea and lens and the axial length of the eye. And what this means is when we view objects at a distance, the image plane is actually focused in front of the neural retina rather than on the neural retina. And this causes visual blur. Myopia is primarily associated with excessive elongation of the eye during development. So therefore, any treatment that wishes to target myopia is really trying to prevent this elongation. The ultimate goal would be to stop excessive elongation altogether, but at minimum, what we want to do is prevent its rapid expression. And the main goal here is to try and stop a child moving from myopia to high myopia. And I'll get on to why that's a problem in a moment. So why do we class myopia as a problem? Well, as this world map shows, it's reached epidemic proportions in many parts of the world. Now, this is most notable in urban east areas of Asia, where between 80 to 90% of school-leaving age children are myopic. Now, some of the models predicted up to the 50% of the world's population will be myopic by 2050, although we are most likely not going to reach that number. But what's worrying is 20% of those myopes have a significant chance of vision loss. That is because myopes are at an increased risk of these chorioretinal pathological changes, which you will all be well aware of, such as retinal detachment, myopic macular degeneration, and staphyloma. And this is best illustrated by this figure here on the right from Flitcroft and colleagues. What you can see here along the x-axis is the progression of myopia, and along the y-axis is the odds ratio of developing either, in this case, a maculopathy or a detachment. And you can see as the severity of myopia increases, the odds with it of one of these two problems increases significantly. What's most important is when someone moves from what's referred to as myopia to high myopia, and high myopia is usually defined as -6 diopters or greater of myopia, you can see that the odds really start taking off for one of these pathological changes. The other major problem is myopia places a significant financial burden, as I've noted here, on health systems worldwide. Here's just two examples from the literature. So in 2010, the National Eye Institute estimated that it cost $14 billion to treat refractive error in the US, of which myopia makes up the largest percentage. In Singapore, in 2013, they estimated it cost $755 million US to treat myopia. So for these social, financial, and health benefits that would be gained by treating myopia, there are a number of labs trying to develop novel treatments for this condition. Now, there are a range of treatments already available to treat myopia, although each has its own limitations. And so what we're trying to do is continuously either revamp those models that are already on market or trying to find new solutions for myopia. The main problem is that currently most of these treatments top out at around 60–70% protection against progression. So none of them really show full protection. And currently none of them are used to prevent the onset of myopia. So what causes myopia? Well, there's two major identified risk factors. The first of these is increased educational pressure, that is excessive near work during your younger years. The second one is limited time spent outdoors, and it's now been shown by a number of epidemiological studies that the more time a child spends outdoors during their youth, the less likely they are to develop myopia. And this figure from Rose and colleagues nicely illustrates this. Up the y-axis is the odds ratio of developing myopia. And you can see here, we've got near work and time outdoors as two factors associated with that odds ratio. You can see that children at most risk of developing myopia are those who do high amounts of near work and low amounts of time outdoors. But if you spend large amounts of time outdoors, you can see that it negates to some degree how much near work you do. So as long as you spend large amounts of time outdoors during your youth, you will, for the most part, reduce your odds of developing myopia. And this will lead on to why we're using levodopa as a potential treatment. Now, following on from that, 2 intervention studies have looked at, therefore, increasing the time spent outdoors and what that does to the incidence of myopia. The first I'm showing here is referred to as the GOAL study. This took 6 treatment schools and 6 control schools of grade 1 students. And what it did was increase the time they spent outdoors during a school day, so not weekends and not on their holidays, but just their school days, by 40 minutes. And that trial ran for 3 years. What they saw at the end of the trial was a 23% reduction in the incidence of new cases of myopia, so a significant reduction in new cases. A second study run out of Taiwan, the ROC study, looked at 1 treatment school and 1 control school. They doubled the amount of time spent outdoors relative to the Chinese trial, so they went with 80 minutes per day extra during the school days, and they ran for a single year. And what they saw was roughly twice that of the Chinese study. They saw a 52% reduction in the incidence of new cases of myopia. So what we saw from this is time outdoors is able to inhibit the onset of myopia. The question comes, well, what is the mechanism by which time outdoors could be protective? And this is important when we start talking about the use of levodopa. And the hypothesis has been from the get-go that it's most likely to do with the higher light intensities we experience outdoors and that light stimulating retinal dopamine release. And so I'm just going to go through some animal data here that shows how this might work. So the first figure I'm showing you here is the correlation between the intensity of light that an animal is reared under and the amount of myopia they develop. So the higher this refractive change, the more myopia that developed. You can see under low light conditions, animals develop large amounts of experimental myopia. But as we increase the light intensity, you can see we can really inhibit the development of myopia to the point where we can actually abolish its development altogether. And that's under here, you can see under a light intensity of 40,000 lux, which is bright, but not even close to what you would actually experience if you simply went outdoors on a sunny day, where light intensities can reach anywhere from 100 to 200,000 lux. Importantly, dopamine release from your retina is also light dependent. The greater the light intensity, the greater the release of dopamine. So the brighter the light, the less myopia we develop, the brighter the light, the more dopamine we release. So it correlates strongly that dopamine may have a role in this protective effect. Now, the role of dopamine in myopia development has been long since suggested, starting in 1989 by the Stone and colleagues group, showing here a reduction in dopamine levels during the day when experimental myopia is developing in animals. So there is a normal control group and the experimental myopia group, and you see a reduction in dopamine release from the retina and a reduction in its metabolite, showing that the system is downregulated during the development of myopia. Most importantly, data generated by our laboratory has shown that dopamine clearly drives this light protection that I showed in the very first figure. So what you see here in the white bar is the amount of myopia that develops under just normal low light conditions in a normal animal facility. You can see that if we then put the animal under bright light, this case, it's only about 15,000 lux. You can see that significant inhibition in the amount of myopia that develops. But if we inject a drug that blocks dopamine's action within the eye, as shown here in the black bar, we completely abolish the ability of bright light to prevent the development of experimental myopia. So the animal models have clearly shown us that bright light and dopamine release are able to act as anti-myopic components. So the easiest thing would be, let's get more kids outdoors. However, there have been significant social, environmental, and educational hurdles that I mentioned here that have really limited the ability of increasing the amount of time a child spends outdoors. The first is weather and temperature. Sometimes it is just impractical to send kids outdoor. There's also issues with pollution or the seasonal changes in light intensity, so that in some parts of the world, the intensity of light will just not be great enough to stimulate dopamine release. But the most important of these factors has actually been educational pressures. And this has been most notable in those areas of East Asia, where there's been significant pushback about the idea of increasing the amount of time a child spends outdoors because it takes them away from their study time. And because educational achievement is so important, this is seen that a lot of the times parents are unwilling to have their kids spend time outdoors, even so it could protect them from developing myopia. So based on this, our group said, well, can we develop a pharmacological agent that simply mimics time spent outdoors by stimulating dopamine release from the retina? And that is where the idea of levodopa is going to come from. So as I've noted here in the first point, pharmacological stimulation of the dopamine receptors has already been shown across all animal species studied to be able to inhibit experimental myopia. And that's usually through intravitreal injection of the dopamine agent. However, dopamine, as I've noted here, is poor at crossing epithelial barriers, and importantly, it is usually rapidly broken down, catabolized within the tissue target. Therefore, most times that dopamine is used to try and treat a neurological disorder, such as Parkinson's disease, the primary clinical treatment is actually administer levodopa, and usually levodopa in combination with carbidopa. Now, why is that? Well, levodopa is the naturally occurring precursor molecule to dopamine in our body. And so it is also able to easily cross epithelial barriers. The transporters are usually there, so across blood-retina barrier, blood-brain barrier. Importantly, it has a slower rate of metabolism, and so it's not so quickly broken down. Now, carbidopa is added to the solution as an inhibitor for premature metabolism of levodopa before it reaches its target tissue. So it's there as a mimic to prevent levodopa being used up before it, in this case, can make it to the brain, or in our case would be to make it to the retina, because that is going to be our target tissue. So therefore, the theory is by administering levodopa or carbidopa in combination, we should be able to increase the synthesis and release of dopamine from the retina. And in so doing, we should be able to prevent myopia by mimicking what naturally would occur if you went outdoors and experienced bright light. Now, the big question comes, well, how do you get the levodopa to the eye? Now, the most common way of giving levodopa carbidopa is obviously through systemic administration as a tablet. However, this would be inappropriate in our condition because obviously levodopa would then make it to the brain and change the amount of dopamine being synthesized and released in otherwise neurologically normal children. And this would cause adverse known side effects with levodopa. Therefore, as I've mentioned here, we need to directly target the eye. And a critical thing about this is by directly targeting the eye, we actually are able to also reduce the clinical dose. As soon as you give it systemically, we have to increase the dose many, many folds to make sure that enough clinically makes it to the target tissue. But if we can directly target the eye, we can reduce the clinical dose, as I'll show you. Now, the most direct avenue, therefore, to treat the eye would be, as shown here, a normal intravitreal injection, which is the common way we use in our experimental myopia models. But this would not be appropriate long-term. Now, the main reason being is that what we're trying to achieve with dopamine and the belief about why dysregulation of dopamine could cause myopia is that dopamine goes through a diurnal rhythm. It goes up during the day, down during the night, and sets many of the rhythms within our eye. And what is believed is by not spending time outdoors, we're not getting that upregulation in dopamine, that proper rhythmic change in its expression. The idea of a treatment would be, therefore, to administer it each day to cause that upregulation in dopamine synthesis and release. And therefore, giving an intravitreal injection on a daily basis would be highly inappropriate and impractical. Sorry, was there a question? Oh, no. The most practical route of administration is therefore topical eye drops. But as most of you would know, administering a drug as a topical eye drop is not easy. Actually, the vast majority of drugs, more than 90% of drugs that have been attempted to be applied topically, actually fail to produce any kind of clinical effect. And that is distinctly worse when you're trying to target the back of the eye, the posterior segment. So anytime you're trying to target the retina, the choroid, the RPE. So most of the drugs that are currently on market that are given as topical eye drops are usually targeting the anterior areas, so either the cornea, the lens, the aqueous areas. And that is mainly because it's difficult to penetrate the corneal surface and also to prevent the metabolism of your drug or catabolism of your drug before it makes it all the way to the posterior area and to the retina. Usually it's also drained quickly from the eye. And on average, a topical drug, only about 3% of it at max will make it to the posterior segments of the eye. However, after considerable formulation testing, we have managed to finally develop a form of levodopa carbidopa in topical solution that can penetrate the cornea and can make it to the back of the eye where it can stimulate the synthesis and release of dopamine from the retina. So what I'm going to show you over the next few slides is preclinical data on the effectiveness of levodopa in the treatment of, in this case, experimental myopia. Now, the animal model most commonly used in our field is the chicken, and that is because its visual system is very similar to that of a human. So the data I'm going to show you on the next few slides is from experimentally induced myopia in that chicken model. What you'll see along these figures is along the x-axis is the concentration of levodopa administered, and up the y-axis is the percent protection against axial elongation, because this is the ultimate goal of any treatment, is to prevent axial elongation. So down this end of the scale, 0% protection means that they develop full amounts of myopia. So they have this excessive elongation of the eye. And 100% obviously means we completely abolished the development of experimental myopia and we saw no excessive elongation. So we started with our proof of principle, which is simply an intravitreal injection of levodopa to prove that it actually could induce an upregulation in the dopaminergic system and that this would lead to protection against experimental myopia. And you can see here a nice dose response curve that as we increased the concentration of levodopa injected, the greater the protection we saw against the development of experimental myopia. And by the highest dose, we completely abolished any development of myopia in terms of axial elongation. But as I noted, intravitreal injections are not the most appropriate way to...
Excuse me, Dr. Ashby.
Yes.
Okay. No, por favor, apaguemos los micrófonos. Okay, please go ahead. Thank you.
Not a problem. As I noted, intravitreal injections are not a practical means by which, however, to treat. So therefore, we moved on to the idea of topical application. Again, concentration of levodopa added along the x-axis and our percent protection up the y-axis. In our original formulation, which we simply took levodopa, dissolved it in solution and added it to the corneal surface as a topical eye drop, you can see we still see a nice dose response curve. As we increase the concentration of levodopa added, we increase the protection against experimental myopia. But this maxed out at about 60 to 70% protection. So nowhere near what that we get with intravitreal injections. However, after playing around with the formulation and including carbidopa in our formulation, what you can see here is that we got a much more effective protection against the development of experimental myopia. And by our second highest and highest dose, we were able to abolish the development or the axial elongation associated with experimental myopia. So we had a topical formulation that clearly could penetrate the cornea, could penetrate to the retina and stimulate a significant amount of synthesis and release of dopamine from the retina. Now, one of the critical things when looking at such data is comparing it to current pharmacological treatments on market. And the primary pharmacological treatment for myopia is atropine, shown here in blue. Atropine has been highly successful in controlling the progression of myopia for over 50 years. Depending on the literature and the experimental study undertaken, that effectiveness is anywhere between 50 and 70% protection against the progression of myopia on a year-to-year basis. What you can see is the dose response curve of topical application of atropine. And you can see it's very similar to our original topical application of levodopa. So they actually share very similar characteristics in terms of corneal penetration, retinal penetration, and the protection they provide. In contrast, you can see our optimized form of levodopa carbidopa is significantly more efficacy, has significant more efficacy than either atropine or levodopa alone. And this is really exciting. It suggests by the animal model, and the animal model to date has translated strongly to the human model, that levodopa will be more effective than the current treatment option in atropine. But the big question is, what about the safety of levodopa when we start talking about adding a new drug to the eye? So as I've noted here, there is already significant safety data in respect to ocular and systemic distribution of this drug when given as a systemic drug, so when it's given as a tablet form. And this is primarily in the treatment of Parkinson's disease, but also in the treatment of amblyopia. So reported side effects include headaches, nausea, low blood pressure, fatigue, etc., as you can see down this listing. Now, most of these adverse effects are seen at the higher doses of levodopa, carbidopa administered to the patient, and usually after chronic treatment periods. Now, these concentrations used are well above that which is required to treat myopia. It can be up to 30-fold higher. And actually, the concentration we're using to treat myopia is below any normal concentration that would be used to treat either Parkinson's or amblyopia, and below even the safety data that exists. And at those lower concentrations when used at Parkinson's and amblyopia, little to no side effects are actually observed. The other important thing to remember is that these side effects are associated with its neuropharmacological activity at dopamine receptors within the central nervous system. So with respect to our study, because we have a significantly lower dose, we have not been able to detect a change in systemic levels of levodopa or dopamine, which I'll show you in a moment. Such side effects are less probable to occur within our system. However, obviously, it's important that we actually test this. And so we've done extensive ocular safety testing, investigating the following parameters. The first thing was drug distribution. When we do target the corneal surface, where does the drug actually get distributed within the body? We looked at ocular surface tolerability and integrity, visual function, ocular health, refraction, and ocular biometry. Now, these were studied by administering levodopa carbidopa at our highest dose, 10 animals per group for a chronic period, and that used both of our models. We used the model of the chicken, which is, like I said, the primary model in the investigation of myopia, and we treated them for 1 month. But we also made sure that there was a mammalian model in there, especially when we started going to the regulatory bodies such as the FDA. And so we used the mouse model, and they were treated for 9 months. In both cases, the animals are given a single drop once per day. What we observed in terms of drug distribution was that levodopa and dopamine levels were elevated within the retina. So levodopa was making it to the retina and causing greater synthesis and release. But importantly, we saw no change in levodopa or dopamine levels within the general circulation, within the blood, following topical administration. And this has been looked at 5 minutes, 15 minutes, 1 hour, and 4 hours after topical application. And I'm just giving you one example here. This is after 15 minutes. This is measured by liquid chromatography mass spectrometry, and it's measuring dopamine levels in the blood. What you can see is there's no difference in dopamine levels between an untreated animal, an experimental myopia animal, and an animal that's given a topical application of levodopa. And this is critical that we're not introducing levodopa into the general circulation where it could potentially make it to the brain. In terms of ocular surface tolerability integrity, there was no intolerance to the drop. So the animals showed no reflex in terms of blinking. They showed no change in grooming behavior. They didn't have their eyelids closed. And importantly, there's no corneal or conjunctival epithelial integrity chaining. So that was done through fluorescein staining. And that's all compared to their control animals. In terms of visual functions, we looked at electroretinogram outputs from the retina and saw no change in ERG outputs relative to control animals. With respect to ocular health, there was no change in IOP. There was no change in retinal thickness or architecture. No signs of cell death indicating apoptosis were observed relative to control. And finally, there was no change in refraction or axial length. And this is actually an important point in the field of myopia. Many of our treatments, be it optical or pharmacological, they will actually be able to inhibit the development of experimental myopia or myopia, but they actually have no effect on normal ocular development. And this actually suggests that the pathways within the eye, there is some type of switch from when we're going through normal development to when we enter myopia that suddenly make these pathways susceptible to both optical and pharmacological treatments. And that's again seen here for levodopa, where levodopa is fantastic at inhibiting experimental myopia, but does not in any way alter normal ocular development. So just to give you an idea of what we have in these data sets, so these are just representative results. In this case, it's the histological changes seen in response to levodopa treatment. So here you can just see a normal retina and a retina treated with levodopa for 1 month. This is chicken. And it's simply been stained with toluidine blue so that we can actually make out the structures. You can see the ganglion cell layer, the inner nuclear layer, outer nuclear layer, the plexiform layers. And you can see that there's no change in architecture, thickness, or structure to the retina. Importantly, what we show down here is there's no tunnel staining. Now, tunnel is a stain used to indicate cells under stress or cells going through apoptosis. The reason both the untreated and the levodopa retina are bright green is because we had to oversaturate the photo just to be able to see the retina because there was no staining. Apoptotic staining would normally look like this. So this is a positive control where we've induced apoptosis or cell death within the retina. So you can see all the ganglion cells, the inner nuclear layer, outer nuclear layers, all starting to glow green, which says that we've induced apoptosis within these cells. So levodopa treatment did not alter the architecture or thickness of the retina and did not induce any kind of cell stress. Another important thing when we're talking about changing dopamine levels is obviously dopamine is a major neuromodulator. And so we wanted to make sure we weren't altering the retinal electrical potentials going on within the system. And so here's just the results from our ERGs. So these are full field ERGs. And what I'm just showing you here is the data for the A wave, which represents the output from the photoreceptors. And what you can see here is the amplitude of the response and the latency of the response, so the time to which it responds for the photoreceptors is no different between a control animal and a levodopa treated animal. So the ERG outputs from these animals, be it the A wave, the B wave, or the oscillatory potentials, were unaffected by chronic treatment periods. In this case, it's the mice, so that's 9 months of treatment with levodopa, so no change in ERG output. So on the completion of this data, we therefore moved on to a phase 1 clinical trial in humans through our therapeutic goods administrator, so the equivalent of the FDA in Australia. Now, this trial was a first-in-human, placebo-controlled, double-blind, paired-eyed, randomized clinical trial, and its job was to assess both safety and tolerability of levodopa carbidopa ophthalmic solution in young adults. In our case, this was males aged 18 to 30. And the reason it was males is in Australia, if you have a new drug formulation and it has not been directly tested for its effects on pregnancy, you cannot use female participants until that drug has been directly tested. So in our case, it is only males aged 18 to 30. And they were treated for 4 weeks or 28 days. They were broken into 2 groups of 14, randomly assigned to the 2 arms of the trial. In arm 1, they were given a high dose of levodopa carbidopa to one eye and the placebo solution to the other eye. In arm 2, they were given the low dose of levodopa carbidopa to one eye and the placebo control to the other eye. Now, the participants were randomly assigned to either arm, but also their eyes, which eye was treated, was randomly assigned. So both left or right eye could have been the treatment eye. They administered 2 drops of the solution, either the levodopa solution or the placebo solution, to the corneal surface once per day in the morning for the 28 days. Our measures were undertaken at baseline, 4 weeks, so the end of the trial, and 4 months after our washout period. But we also did a subset of measures within the 4-week period at 1, 2, and 3 weeks. And this just lists the measures that we undertook and when we undertook them. So for ocular tolerability and anterior surface integrity, we looked at tear film osmolarity. We had the participants undertake an ocular surface disease index questionnaire. We looked at tear film breakup time, corneal and conjunctival epithelial integrity. For visual function, we did multifocal electroretinogram, we did perimetry, and we did high and low contrast visual acuity. For ocular health, we mainly did OCT measures to look for retinal thickness, choroidal thickness, and so forth. And we also looked at intraocular pressure. And with respect to refraction and ocular biometry, we did cycloplegic auto-refraction and also OCT measures of ocular biometry, axial length, corneal thickness, anterior chamber depth, and corneal curvature. Now, the critical thing to note here was that we saw no change in any of these components over the length of the trial, either between baseline and 4 weeks, baseline and follow-up at 4 months, and between 4 weeks and 4 months. And this really matches with both the historical human data from systemic taking of levodopa, but also the animal data showing that there is no adverse effects associated with topical application of levodopa, carbidopa at these extremely low concentrations. Now, just to give you a feel for this data, rather than me simply saying no changes were observed, this is the idea. This is ocular surface tolerability data showing corneal staining and conjunctival staining with fluorescein. And what you can see is there's no indication of epithelial damage or scratching or drying out. So you can see the corneal staining over 0, 1, 2, 3, 4 weeks, and then the 4-month follow-up. And the same is for conjunctival staining. We do have this oddity where at 2 weeks, all groups show this downtrend. And we're still trying to work out what that actually means. But you can see by week 3, it's back to its normal baseline level. Here's some representative data for ocular health. And this is just showing retinal thickness between the groups from their baseline to their end of measures at 4 weeks. There's our placebo eyes, placebo 1 and placebo 2. So that'd be placebo 1 for the high dose group. Placebo 2 is the low dose group. High dose actual drug group, low dose actual drug group. And what you can see is no statistical significant changes in retinal thickness from baseline to the end measures for these groups. And finally, just to give you a feel for safety in terms of refraction and biometry, what I'm showing you here is there was no change in axial length, corneal curvature, or cycloplegic auto-refraction. One interesting thing that did occur is that in the random selection of participants to the 2 groups, you can see that there was a difference between the low dose, and the high dose group at baseline refraction, but their refraction maintains the self in both groups. So in conclusion, levodopa was found to be highly effective against the development of myopia in preclinical studies. With the addition of carbidopa, levodopa was able to abolish the development of experimental myopia, providing greater protection than that of atropine, which is the primary pharmacological treatment for myopia currently on market. Levodopa eye drops are found to be safe and tolerable in both preclinical and human phase 1 clinical studies. Therefore, this ophthalmic solution is ready for phase 2 clinical trials, and we have a number of potential sites currently being established for such trials. So our strongest hope is that levodopa will become a powerful treatment to help prevent the onset and progression of myopia. And it really does have a really strong potential to act as a prophylactic, in which we can determine kids that are pre-risk to developing myopia and start having them be treated with levodopa, which is a naturally occurring compound within our body. The hope is, therefore, we never see onset and that we don't have to deal with simply trying to inhibit progression. So on that, I'd like to thank you for listening and thank the team that's been behind generating this data. Thank you.
Dr. Ashby, thank you very much for your very interesting talk. And I am impressed because you made it very easy to understand, because it is not an easy topic. And it seems to me it has a huge potential, as you stated, because you have already proved that it is effective, both effective and safe. So congratulations. And I think that the only question that I have is, how can we participate on the phase 2 studies? It would be great.
I'm happy to talk to anyone about participating in phase 2 trials. And frankly, the more sites, the merrier. One thing that happens in the myopia field quite often is that a single location undertakes these studies, and that later duplication of those studies are difficult. And so the more locations that undertake phase 2 clinical trials, the more powerful the data set will be at showing that there are no differences due to location and so forth. So if anyone is ever interested in undertaking a phase 2 trial, I'm happy to talk offline about being part of that.
Perfect. So do you think that it will replace the other options, the other or anti-myopia treatments like Atropine, or do you think that it will be possible or there will be a room to combine some therapies?
Look, I think currently there are a number of very good options on the market. So you've got things like the DIMS lens that already exist. You've got Atropine that all do a very good job at inhibiting progression. If Levodopa stands true to what the animal model says and that it can produce greater protection than these other methods, then absolutely, I think it will become a leading treatment. But there's a while to go before we will know its effectiveness in the human condition relative to the current treatments. There are a lot of groups now trying combination treatments, especially lenses with pharmacological agents. There's many groups out there using things like orthokeratology with 0.01% atropine, or things like the DIMS lenses or the MySight lenses with atropine, trying these combination therapies because there just seems to be this glass ceiling of between 60%, 70% progression prevented. And they don't seem to be able to really push above that. And so the idea is that combination therapies may take us above that area. But there's also a lot of kids that are non-responders to all these different treatments. And so the more treatments we have out there to try on these children, the better.
Dr. Ashby, thank you. We have here
I have a question.
Dr. Vanessa, go ahead.
Doctor, is it known how dopamine acts to inhibit the increase in axial length?
So we know how it acts within the retina. We don't know how the final message makes it to the sclera and therefore inhibits this growth pathway. So we've started to get a really good understanding of the pathways within the retina that dopamine functions. Dopamine is unlikely to be the messenger sent from the retina all the way to the sclera because you've got to cross the choroid, and it's still unclear how you would make it across the choroid without being diluted or washed away. And so people are still trying to understand what the mechanism is forward, but most likely dopamine binds somewhere within the RPE and stimulates a pathway that then moves to the choroid, causing the known choroidal changes within myopic eye. And then from those choroidal changes, somehow a signal makes it to the sclera. But that pathway is yet to be determined.
Okay, thank you.
Dr. Ashby, we have had some experience combining atropine with ocular hypotensive eye drops. And it seems to us that it works like some kind of synergy. Of course, there is very scarce evidence of the effect of hypotensive medication, but some experimental and studies have found that they can have some effect slowing myopia progression. What do you think? Do you have any experience studying ocular hypotensive?
So these hypertensives are a very interesting grouping, and I'd actually be interested to see where that area of the field goes. Currently, the animal data is inconsistent between the studies I've seen so far, and that's usually just because of the size of the studies, the N values they're using. But also what I've seen is between the different studies, there seems to be a different mechanism underlying it. Now that might be species to species differences that they're using, but we don't have a good handle on exactly the mechanism by which those drugs are functioning. So it's an area that definitely needs more research, but there are promising signs. There are definitely promising signs. The literature is clear on that at least. But the mechanism, and this is a big thing, it's, for example, atropine is used by millions of kids worldwide right now. We still don't know how atropine functions. We had our original hypotheses that's been long since disputed or let go of. And there are multiple hypotheses now about how atropine actually functions within the eye, but we actually don't know. Now, if you knew how some of these drugs work, you can refine them. You can get more powerful drugs, more defined drugs. And atropine, as a perfect example, has a number of known side effects. you could remove those side effects potentially because it's such a broad spectrum drug. It does so many things within the eye. So understanding the mechanism by how these things function is really critical. And that's one of the great things about levodopa is that we know so much about how it's functioning. Yes, we don't know how dopamine gets to the sclera, but we know it's the dopaminergic system working, and we have plenty of data about how dopamine works within the eye.
Ashby, thank you again. Tonight for us, we have Dr. Lisa here with us in the audience. Her group has been studying also another approach using red light, low level red light applied to the retina. Maybe it could be also, maybe it works also increasing dopamine in retina could be an option. And yeah, could be an explanation of how the mechanism of action of such treatment.
Absolutely.
Hi, Professor Ashby.
Yeah.
Sorry.
No, go for it. Please go ahead.
Hi, Dr. Ashby. This is Lisa, and I'm a research fellow of Professor Mingguang He. And so we had a close connection with Professor Ian Morgan. And last week, I gave the presentation about our recent clinical trial in terms of the efficacy and the safety of the repeated low-level red light therapy in myopia control. And I heard about that you were gonna give the presentation this week. And so I'm really honored to be here as an audience, and very impressive presentation. And can I have a quick question?
Of course.
In terms of the safety about the ocular surface tolerability, and I found that in the second week we found the reduced the conjunctiva staining score. Are there any explanations for this reduction?
No. So what we assume is because we have a team of clinicians. The person undertaking the staining test that week was a different clinician to the week's other. And so I assume it's clinician to clinician differences. And that's one of the problems with staining. It's subjective. It is up to the clinician to judge it. So what's more important that it's one clinician seeing all participants, that it's not different clinicians seeing the different participants at each week. And so that's what we're putting it down to at the moment. But we need to look into it further. The main thing is that there was no difference between any of the groups, and that they all returned the week following to their normal levels when it was the primary clinician was back making the measures. Sure.
It may be due to the observer variations. Okay.
I think so. And that's the tough thing in all these studies. So 50% of our measures are subjective, 50% of our measures are total. And so obviously things like ERG recordings, they are what they are. But things like corneal staining is a subjective measure. And so its primary job is that the clinician is the same between participants on that week, so that there's no variability between treatment and control groups purely because you had two different clinicians looking at them.
Okay, thank you.
Not a problem. And by the way, the red light story, very interesting. As someone who started off his career a lot on light and the ability of light to stop myopia, any such treatment would be fantastic. I've long said, and Ian will attest to this, that I would love to see a bright white light system also tested, but the data generated on the red system is extremely interesting. Obviously, that's going to create a great debate within the field, because animal models have shown in some that red light is myopogenic, and in other animal models, it's anti-myopic. Obviously, the human is the final test, and you've shown clearly that you can inhibit myopia with that system, which is very exciting. But yeah, it's going to create great debate within the field about why some animals become more myopic under red light and some animals become less myopic under red light.
Yes, that's true.
Dr. Lisa, thank you for your contributions, and also thank you for your talk about red light, very interesting also. And Dr. Ashby, thank you again for your very, very interesting talk, and Have a very nice day for you in Australia, and we will be in contact with you.
Thank you so much. Thank you for the opportunity to present.
Thanks a lot. And thank you, everyone. And we will keep you updated. Bye-bye, and have a very nice day for you in Australia. And buena noche para todos aquí en Colombia.